Okay, I'm gonna zoom, not listen anymore.
You have something else?
No.
Okay.
Good.
So for the material that I'm going to be focusing on is lead halide perovskites, where in this situation you have the lead in the center, you have a halide in these red, where the blue are monovalent cation, typically methylammonium or cesium. So the reason we look at these materials is they have good tunable, the band gap is easily tunable based on the size and the specific halide that you use in the material. They have good stability. That's not quite right. They have enhanced photoluminescent quantum yields.
Enhanced from what? Should it just be high photoluminescence?
Yeah, probably.
Or if you do not know in respect to what, say, to conventional materials, but be ready to answer what conventional materials are.
So okay. And they have long charge carrier lifetimes, so they can diffuse the charge. The charge is diffused better for photovoltaic applications. Some of the cons for these materials are the crystal phase transitions, and this affects the stability primarily to their thermal and photo stability. They have poor stability toward moisture because this is an ionic solid. It tends to decompose.
What's the last bullet on con?
The last one, I'm reading it and I don't need it because I covered it in the first bullet. It's the high temperature crystal phase transition. So the reason that we're so interested in perovskite materials is that they have a wide range of colors that they can emit and absorb. And the precise...
David?
Yep.
Previous slides were creating implied impressions that they are solids, periodic solids with unit cells. Your next slide shows beakers with something in solution.
Yeah.
How do you make transition? Even if you do not have transition, tell.
Should probably put this slide before that is that, where I talk about the different dimensionalities.
Yeah, do whatever you like, but just announce that.
Okay.
Here are solids and here are colloids that are dispersed.
So,
But he also already mentioned tunable band gap, and he said quantum confinement and cation. So then you could leave your slides, and if you just say, let's talk about tunable band gap, here's one way to do it, and that's through quantum confinement.
okay.
So no one is criticizing the content, it's only the arrangement so that it flows.
Yeah, and there's a few things I'm not sure if I like how they're arranged at the moment. So the way that we adjust the band gap is we adjust which halide is present in the material. In addition, we adjust the size So for these materials, they range from 5 nanometer to 15 nanometer.
What's the borax time radius?
Just write down the question and he'll
Okay.
I do not remember. I do not remember that one offhand.
That's fine.
David, you mentioned articulated verbally that only size is changed, and your figure shows composition difference.
So
Chlorine, bromine,
yeah,
iodine.
the halide will change as well.
Just say both size and composition help
Okay.
to tune.
And the reason that they are so popular in photovoltaics is that if you look over here, you can see the red circle with the yellow center is the perovskite solar cell. And we can see that since it was first made, it has had a very rapid increase in efficiency. And
Is it okay?
yeah.
So, at which point you plan to define the difference between photovoltaic and light emitting applications? Because right now you are focusing on photovoltaics, and previous colloidal highly likely was connected only to photoluminescence.
Yeah. That was
Just plan when to declare.
okay.
And
So
if
my idea is that when I was talking about why we were looking at them to include both, and then transition to photovoltaics, and specifically when I started discussing it.
Okay, and again, there is no criticism, and audience will. You can be very versatile. Tell from the very beginning. There are two applications,
Okay.
and I'm going to explain what are the differences in the middle of the talk. And if you announce it, no one will stop you.
Okay.
Another question off of Dimitri's is, you talked about 0D, but your title only says 2D.
Yeah.
Is there, I know there's rationality on why to include it, but are you going to articulate your rationality in including 0D materials?
I hope so.
Okay.
You may include a section of the. Can we go back to your slide number 2? So in your quantum confinement, you can quantum confinements column 0D, 1D, 2D, 3D, and then maybe make circle around 2D, telling that, yeah.
But
I'm going to introduce all 4, but we will focus specifically on 2-dimensional.
if you do that, it might be prudent to move slide 5 to where you talk about quantum confinement.
Okay.
Does that kind of make sense?
Slide 5 is my dimensionality slide, right?
Mm-hmm.
Yeah, band gap tunability. Because that's more to do with quantum confinement than it does kind of with your introduction.
Okay. That makes sense. And so the efficiency has been increasing fairly rapidly since it was first made, and is now just over 25% efficient for.
Which line are we looking at?
So we're looking at the red circle with the yellow center, which we can see the percentage is right there.
I invite you to look at the red circles.
Red circle with yellow center, because there are red circles with other centers. So here we see the different dimensionalities that are present for the materials. In the 3D, we have a bulk structure, and it's periodic in every direction, in all three primary directions. Didn't explain that yet. I think I moved slides wrong. In the 2D, it'll have a thin film structure, and with the picture we have, it would be a film in the plane of the screen.
Isn't it called the plane?
So it'd make a film in the plane of the screen.
Are you sure it's not perpendicular?
It could be perpendicular as long as z-axis is one of the periodic.
But you have your inorganic insulator between the purple and purple. So if it's with the plane, then your insulator is included in your...
So yeah, the insulator is going to be periodic as well. So it's going to repeat. So this repeat like this.
Yeah, so then if you go up and down on the screen, that is confined. So the non-confined region is out, right?
So
you have this.
I'm trying to understand exactly.
This is what you have
Yeah.
plotted. And you're saying that the planes go with the screen?
Yeah.
But on the papers, the planes?
No, the plane, the papers will act as an insulator in.
Maybe I'm just not seeing it right.
In our cell here, actually, it actually repeats with these organic spacers separating it. So you have on either side of the screen, one side will be the electron transport, one side will be the whole transport layer. If we would think about it like that. Am I understanding that right?
I guess when I look at it, I see it differently, but I'm probably wrong.
I do have a quick suggestion for your consideration. Look at your nice image here, where it is a schematic diagram with a little pizza boxes. So let's go to your slide 7, or different dimensions. Yeah. So it looks like through your previous talk, you were attached to this figure from probably this paper.
So I chose it simply because the
But,
other figures match it.
Spend maybe 10 minutes, add one more slide in front of this, and make your personal hand drawing or boxes out of PowerPoint to do schematic introduction.
Okay.
What are dimensionality?
So yeah,
You first teach us what is dimensionality, periodic boundary conditions, and 0, 1, 2, 3 dimensions, and then tell, now look at me, I will apply this concept to perovskites.
Okay. So yeah, the way I understand it, this is going to be the layer. It would be like the screen, and it would be what we're stacking on is going to be in front of and behind the screen.
Okay.
And I actually sat a little bit with this figure, and that's because I was trying to figure out exactly how it was showing, and that's the conclusion I came up with, which is different than the 1D conclusion. In the 1D situation, we have they form rods, and you can actually see 12 different rods here coming in and out of the screen.
It is correct if audience knows what to expect.
Okay.
Maybe you make, with the slide before that, make it very explicit, just make one rod. So it's definitely rod and nothing else.
And then the 0D is ones where it's constrained in all dimensions, forming a quantum dot. And in this picture, we have 5 ones shown.
But it is the absolutely minimalistic zero-dimensional object, including only one d-valent cation,
Yeah.
right? And quantum dots do not need to be.
Quantum dots
this
can
small.
be larger.
Yes, but if you do not articulate
So
it,
I need to explain this type of thing earlier is what we're saying, right?
whatever you like, but it could be reasonable.
Okay. So the perovskites can form three different phases depending on the temperature. So you have the cubic phase where it's set up in a cube. You have the tetragonal phase and the orthorhombic phase. And which phase it chooses is dependent on the temperature and dependent on the size of the specific anions and cations that you have involved. And the Goldsmith tolerance factor here talks about that, and I need to explain that. So I'm not sure this is a good place for this slide. Just saying what. So as we look at the perovskites, the 2D layers, 2D layers form when they're forming. We have a few different configurations they can make. One of them is the Ruthenium phase, and in this one we have our perovskite cells, and they're spaced with cation before we have another perovskite cell and then spaced with another cation. So the difference between A and B here is the size of the perovskite layers. In A, we have a single perovskite separated, and in B, we would have two. So in our general formula here, N would equal 1 in A and 2 in B. And one thing to note for Ruthenium phase perovskites is that as you go between the different perovskite layers, they are offset from each other. Where in Dion-Jacobson phase perovskites, the perovskite layers line up with each other. And one of the major differences between Dion-Jacobson and Ruthenium is in Dion-Jacobson we use divalent spacer ions.
You teach, right?
Yeah.
So do you watch eyes of your undergrads? Make sure that audience is not losing you. And this place is a little boring. Try to make some entertainment, or I cannot articulate what is specifically boring. Probably it's big logical gap. You jump to specifics without telling the basics.
Okay.
Majority of audience are practicing experimental chemists or biochemists.
Which is something I need to do in these two slides.
You may just introduce. It doesn't necessarily. You do not necessarily need to have specific slides. You can explain it by hand waving how the fabrication of colloidal structures is performed.
Okay.
Have you done it before yourself?
Not off the top of my head.
Take consultation from Aaron and from you.
Okay.
So it's I do not speak language of experimental chemists, but it is like a goose with three necks, round, whatever.
Round bottom.
Yes. And one injects precursors that in right proportions, and they start to nucleate. And colloidal chemists and inorganic chemists know right language for like building this unit cells one after another. And then when stops injecting the precursors for good stuff, and with syringe injects different compounds that surfactants block the surface from further growth. And then when turn off the heater or does some other things. And if you speak a little bit in this language, majority of audience will appreciate it very much.
Okay.
And there are tons of highly cited videos on YouTube how this is done. And then after you do this, everyone will think, oh, I understand everything. I am an expert in what he shows. And then you tell, and now just little thing, change ratio of the precursors, and instead of zero-dimensional quantum dots or three-dimensional bulk, you get some magic wonder structures with super properties.
Okay.
Okay, sorry for interrupting. Please keep going.
Interrupt all you want. So, what the organic inorganic hybrid perovskites are is we, instead of having a metal spacer ion, we have a organic spacer anion, and there are some examples of what we have here. And if we look at it, you have your perovskite layers, and then they're separated by the linker cation. So for the Ruddleson poplar, which these ones are depicted as Dion Jacobson, for the Ruddleson poplar, you would be looking at anions that are monovalent, where the Dion Jacobson, we'd be looking at divalent anions, so they could link both sides of it. And in these cases, it's the van der Waals interactions that would hold the molecule together. So the reason that we're interested in this is that these organic spacer molecules act like a insulator, creating multiple quantum wells in our final molecule.
So if you change the organic linker group from small to large size, do you expect any changes in the stability, or are there any other properties?
So there is stability issues involved with them. They do tend to become more stable with larger linker groups, because that's primarily assumed to be due to the hydrophobic effect of the linker group. It also depends slightly on the size of the perovskite group. If the perovskite group is too large, it'll start acting like bulk once again. So the reasons we would want to use perovskites for photovoltaics is their long carrier lifetime. So they have a long time for the charges to move through the circuit.
Do you know why? Is there a fundamental reason why that is the case?
In the 2D hybrid perovskites, the organic linkers make it I can't think of the word I'm looking for. In the 2D, the organic linkers suppress the mobility of the electron and hole, slowing down the recombination. I do not offhand know why that's true in bulk, though.
And this is only for 2D materials, because throughout your presentation, you use perovskites as like bulk perovskite. So is this only for 2D materials? Or is this for all perovskites?
This is actually primarily for bulk perovskites, although.
Then if this slide is about bulk, then do not hide it.
Okay.
So no one will criticize you for being fair and open. Just be certain.
Okay. Need to rework this slide entirely by the look of it.
What is dielectric constant of perovskites? Just order of magnitude.
Don't remember.
But is it like 1, 10, 100, 1,000, 10,000?
I remember, was it 10?
10?
Any other opinions?
Closer to 10,000.
Remembering 10 at least.
What's a dielectric constant of water?
I believe it's around 80, right?
What?
I think it's like 79 something.
What is dielectric constant of vacuum?
So is the dielectric constant one reason why the carrier lifetime is so long?
Maybe.
So they also have a tunable band gap. In the bulk, this is primarily achieved by adjusting the constituent ions, where in the lower dimensions, the size also plays a factor.
So I have another question. On slide 4, you don't need to go there. You have lead halide perovskites, and then you have pros and cons, and a lot of the pros and cons you've already mentioned.
Yeah, that's what I noticed when I was re-looking at this slide right now.
Oh, okay. So
I would replace this slide with like a follow-up from your previous slide. So like, you say you can synthesize a bunch of these with different linkers. And
Give some.
you should follow up on that and be like,
This
what
is
would
how.
be good, or maybe not how, but like what would be a good linker for
Okay.
a solar cell? Since that's like the main application.
So the one major thing that I list here that I didn't list in the early one is the transition from the laboratory scale to the industrial scale or commercial scale. I don't know why there's a random red dot on it either.
Can I say something? If when you are done with addressing suggestions and questions that probably all of us are writing, and if you have free time, which I doubt, there is an exercise that could be really helpful for organization and presentation. Make a flow chart of all chapters of your talk and make arrows just for yourself.
Okay.
How they are connected, how they flow from each other. And by doing this exercise, you can swap the order and think visually on the how to organize it.
Okay. So this slide should definitely be earlier. So what I have here is a schematic representation of a solar cell, and we have what a solar cell works like. You have a transparent anode, whole transport layer, your active layer, which in this case would be the perovskite, and an electron transport layer followed by a cathode. So as the light comes in and hits the active layer, you excite an electron, and then the electron will move through the electron transport layer into a circuit that comes around and recombines with the hole over here. So when you turn on the light, you have an electron that moves around and turns on your light bulb. So some things that could be used for this is where I'm going with that statement. Oh, forgot I added that again. And just for a visual representation of how these two-dimensional perovskites would fit into our solar cell, they're going to be set up so that the organic linkers separate the perovskite cells from each other, but that the electron transport and the whole transport layer are connected to those cells on either side. So, yeah, I'm going to look at some environmental stimuli for these. So, for the one thing that they are susceptible to is thermal decomposition. And as we look here, this first graph shows heating steps in red and cooling steps in blue, where they first heat it up to 350 and then let the perovskite reversibly
regain its properties.
regain its properties. And they found that once you heat it to 450, it starts having a decrease in return on how much it gains the properties back. And every heating step is 50 degrees warmer than the previous one. And they let it cool down to the same temperature for each step. And in our second graph here, we're looking at methods to prevent this degradation. And the blue line here is bare perovskite. This is 0D perovskite. Where the red line is perovskite in a mesoporous encapsulation technique. And we see that the mesoporous technique decreases the effect of thermal stability. So, and this is where I was thinking that slide on cubic versus orthorhombic versus others should go, because that's where this is an issue. And that is actually dealing with the substitution. So the Goldsmith tolerance factor for these varies and affects the shape of the molecule.
So what happens to the, what's the visual appearance of perovskite?
It's a black material.
And what happens if you heat it over 700 Kelvin?
It'll turn clear.
Why?
Because it decomposes into its constituent parts.
Good enough?
Yeah. Which don't absorb,
Okay.
at least not in the range we can see.
Well, can be yellowish, like lead iodide or lead.
Yeah.
It's yellowish.
So how does this slide relate to 2D perovskites?
It really doesn't.
So you might want to put this one in the intro,
Okay.
maybe.
That would work with the.
Yeah, it'll just show one of the stability issues that 2D perovskites should be able to overcome, or could potentially overcome.
Okay. Because yeah, both of these figures are 0D.
So quantum dots.
Yes.
So I have a general comment / question. What's your motivation?
Just get great and forget about it.
I feel like they wouldn't accept that motivation.
No, like that's your intrinsic motivation, like for you. But what is this presentation's motivation?
Show that 2D perovskites give a good compromise between stability and efficiency.
So where has that been stated or compared?
At the moment, nowhere.
So like we go through 12 slides before we go to like photovoltaic cell.
Okay.
And if I didn't know much about this, so let's pretend I'm in Dr. Soon's group or Sibi group, and you go through 12 slides of this is what a quantum, this is what a perovskite, this is blah, this is blah, this is blah. Do you think I'm going to be around to get to the slide about photovoltaics?
Probably not.
And if your entire purpose of this presentation is to say materials are ideal for photovoltaics, and that's what you want me to get at the end, do you think I'm going to understand that from listening to your presentation?
Not overly.
And I think part of your grade, if your motivation is to get a good grade in it, is dependent on the students filling out, oh, they did this right, they did this right, they did this right. So it might be good to add a few slides of motivation right after you do your introduction, environmental stimuli, quantum confinement, and conclusions. Because as of right now, if I had to look through your presentation, I probably would not be able to say 2D materials are ideal for PV applications.
Okay.
And I don't say that to be harsh.
I can see that.
Okay, because like I want you to do as well as you can.
Yeah.
Great comments. And another note: no one will grade you on the quality of the results from literature. They're not your results. It is what it is. But you will be graded on your skill to sort and logically arrange them in a consequence. So if something is unknown, the community doesn't know the answer. It's an open question.
Okay.
That's fine. But here is the logical sequence that connects things to each other and bring us to something most interesting.
So getting back to Dimitri's earlier point where he's like, draw the arrows, I would almost say that is more important than working on individual slides, because
Okay.
if the ordering is completely out of whack, then it's still going to be weird. And in that case, you can say, oh, this slide deals with this. And then if you have that correlation, you can say, okay, I want to bring home this point, this slide does that, it follows up by this, right? Does that kind of make
Okay.
sense?
Yes, that makes sense. Yes.
Yeah.
And
Because sometimes if you have slides that are nice, like the one that is slide 8, I think, where you do different phases.
and that's really related to this.
Yes, but at the same time,
It could be both phases and decomposition.
yeah, so like this slide's nice, but is it needed is another question. So like you just throw it out and then it's just sitting there.
Yeah, that's why
You do need it.
I do think it needs to be. I think it needs to be next to this slide, because that was actually the last slide I added before I sent it to Dimitri, because I decided it was needed.
You just have to explain it more, because like, based on the phase, it changes whether it's good for a solar cell or not.
Yes, but just having it here doesn't tell you anything about the application.
Right.
So maybe even if you slid down the relative intensity versus temperature to the right, slid that down a little bit and made this figure smaller and plopped it there, then you could say this has 2 reasons: it decomposes and it changes it changes phases, which causes the PL to die.
Okay.
But yeah.
So as we look at light and moisture stability, and these ones, the red lines represent the 2D perovskite, where the blue lines represent the 3D or bulk perovskite. And this paper is using an encapsulation method to test to see how well it can prevent these issues. So with illumination or photostability, the major issue is thought to be that it decomposes and creates trap states in the material. So if we look at the top figure, which is unencapsulated perovskite, we see that the bulk drops to almost zero efficiency within about 500 hours, where the 2D perovskite maintains approximately 60% efficiency. But in the encapsulated, the bulk has a similar form, but the 2D maintains a high efficiency throughout the experiment. Where in our moisture stability test, we see that the bulk decomposes rapidly in approximately 10 hours to virtually no efficiency, where the 2D maintains some efficiency for longer. But in our encapsulated trials, the 2D maintains efficiency much longer, going up to, I remember that last one is about 2,500 hours.
How many days is that?
100? 1,000?
Like 100.
100.
So
Somewhere
3
around.
months.
Yeah.
What is PCE?
Cell efficiency,
Our
power
conversion.
conversion efficiency.
Why unprotected decomposes with water?
It's an ionic solid,
Uh-huh.
so the water is a polar material, and it breaks apart the perovskite layer.
So what does it mean, breaks?
It decomposes
Dissolves?
dissolves the material. And the reason that our 2D models take longer is because there's an additional organic linker that acts as a hydrophobic layer.
So you may try to reach to a broader audience, telling like both lead and bromine ions are to some extent soluble in water, and as soon as it is exposed to water, they start making these complexes and running away easily. What will be the most stable complex of lead ion with water? Like, would it be octahedral?
I think so. I'd have to look that up though.
You may even scratch it by hand.
I assume it would be a hexa-aqua lead.
Yeah, draw it and tell that hexaqua lead departs, and it's a dynamical solvation of layer by layer.
Where would the halide go?
Halide would also dissolve. It would,
Basically, that's kind of outside of my realm of chemistry.
that would be my assumption, is the halide would dissolve and the lead would dissolve. And I'm assuming hexa-aqua, but I could see it being tetra-aqua.
The
The lead.
lead would be attached to the oxygen, and the other one would be attached to the hydrogen,
Yeah.
right?
So,
If it's like a 1-to-1 ratio,
Not 1-to-1. It
Yeah,
will
it-
until enough waters will come, and then it
Yes.
will tear off.
yeah, so the lead should go,
that's not a pretty depiction of water, but
is that LB?
yes, it is for some reason. That is not the right
So-
symbol, but
Letter P is replaced with letter L.
Yes. So like lead would interact with the oxygens, and then the halide would interact with the hydrogens, right?
yeah. Why can't I draw the plus? I can't draw that plus for some reason.
Yeah, it does. Okay.
So yeah, it would separate out like that. So it's the water is going to form a shell around the ions, like if you were to dissolve sodium chloride.
Okay.
So here we look at the stability of the Ruddleson-Poplar model just versus the bulk. And we see in, what does this go out to? 1600 hours is the final mark over here. We see that the Ruddleson-Poplar, which is the red, loses its efficiency slower than the bulk. Some factors that affect this is how thick the film is. So the thicker the film, it's going to decompose slower because then it has to go layer by layer to decompose it.
Or opposite, thinner film to decompose, because it will dissolve first layer and then it will stop at the organic protective.
And the choice of the organic ligand, as we were talking about earlier, will also affect the stability. modifications to this slide.
It's kind of a question that you may answer at that time.
I was intending to make those modifications myself, I just hadn't done it. So the quantum of confinement effect, if we look at the band gap for our quantum material, can be visualized as the bulk band gap plus an additional difference in energy, which can be approximated by particle in a box. And if we look at the different dimensionalities, we'll have different levels of confinement. So in 0D, it'll be confined in all three directions. In 2D, it'll be confined in one direction. And if we look at the material, we see that there is the energy near the bottom, that n equals 1 in this situation would not be zero energy. So we have an additional energy right away.
And can you go back? So how this additional energy depends on the size of your thickness of your layer?
The thickness of the layer is going to affect the size of the box, which in our equation here is represented by the L. So a thicker box or a bigger box is going to make the energy difference smaller.
Okay, so if you need to increase the energy, you need to take the thinner layer.
So a thinner layer will increase the energy more than a thicker layer will.
So I know what's on your next slide. This doesn't relate to that at all.
What?
It does, but it doesn't. So you have a finite well where the barrier size is your insulator, right? So,
What, please repeat?
so the next slide, this one,
Uh-huh.
you have a finite well that is repeating. The previous one is an infinite well that does not repeat.
Okay.
Do you
Wait.
think-
How do David? Can you please show here in this slide where is insulator and where is semiconductor, and then let's check if Levi understands.
The
So
red is your
The pink here
well,
is the semiconductor, which
the other
is the
stuff
well,
your barrier.
and these grayish lines that are relatively hard to read are the organic layer, which acts like the barrier.
So we agree on that.
Yes,
Okay.
but
Now it's a question.
this is an infinite well, not a finite well. Which these are finite wells that are
Oh,
repeated.
that's minor correction. The only difference is the size of the well. The
No.
correction of finite and infinite well is very secondary. The size is much more important than the height of the well.
Okay. Okay.
That's a good point.
Yeah, you have three generous 3 minutes.
So then, this is an approximation of the effect here.
It's okay, it's no secret. Everything is cited.
So if you go to your next slide, can you point which of your toy models corresponds to the spectrum?
So if you look at it, each one has an increasing layer of n. So we start with n equals 1 and go to n equals 7. And the purplish color on both graphs is n equals 1, where the redder color is the red is actually bulk, where I think it's orange.
So your
Orange is the n equals 7.
your right lower panel, yeah, on the top of this panel.
Yeah.
Top of it has numbers.
Yes, it does.
Can you bring these numbers to the attention of audience
Okay.
and just articulate what they are?
Okay. So if we look at the top here, we have the what N equals for each color, going from 1 to 7, and then bulk, infinite for bulk material.
So the larger the number, the bigger is redshift.
The larger the number, the bigger the redshift.
Good.
So, in conclusion, the perovskites are an emerging material that show good promise for their use in photovoltaics. Their stability issues are our current major challenge to using photovoltaics. But it does appear that the 2D perovskites are more stable than the 3D perovskites. And going back to what Levi said a while ago, I need to add a slide that actually compares efficiency. It's about 25% efficiency for bulk, 13-ish for 2D right now.
But bulk efficiency will not grow, and
The bulk efficiency still can grow, but it's starting to slow down its growth. The estimated is 31-ish%, if I remember. I'd have to look that up again. And by changing the size of our perovskite layer, we can fine-tune the band gap for our materials.
Done? Okay,
Acknowledging my built.
So, please, since we have the second talk, write down if you have some questions that David didn't answer on the notes, and David will collect and use it for improvement. We have a special.
You leaving?
Yeah, I teach.
Oh, yeah, you have to go. Yes, you do.
It's 5 o'clock now. So you have to teleport. Go tunnel.
We do have a special guest, Professor.
Take it one.
First, that's to the end. Why is it at the end?
Else I can go.
We're going in inverse order.
You can
We're starting at the end and going
through your
backwards.
So there are some open challenges in experimental research of metal
Does this laser pointer have a different? Why is it? Is there
we do not take
missing? It's missing the little
complaints because
focuser.
it's from the.
You want to buy
series.
this one? This one's a bit better.
But
it doesn't-
can I? If I move here, does it move there? Yeah, sort of. Oh, it does, but it needs a mouse pad or something. What about this? Does it work now?
Do you want to write?
Well, now it kind of works. It kind of works. I typically write, but it's okay.
Because
That's,
it's a touch screen where you can write.
Is it a touch screen?
Yes.
Can I write with the Sharpie?
No.
There is a,
Is there a pen?
yes.
Oh, okay. So that's something. That's something. I don't need that though.
So we do not want smiling faces on your talk.
No, it doesn't need a smiley face. This is at least I threw together in the past few hours. If I was planning on just giving a chalk talk, but there's no whiteboard. There's no whiteboard, so a chalk talk doesn't work. Not a chalk talk anymore either. It's Sharpies. It's sad. It's nice feeling the chalk. Anyway, I'm here to talk about something I need help with. So as you may know, my group studies oxygen as a terminal oxidant. So oxygen has a reduction potential 1.23 volts. If I do that, it doesn't. But then I can do this. No, because then it still thinks it's the okay. That's fine. We'll make it go. Great. Which is plenty to do a lot of cool chemistry. So we can oxidize a bunch of cool things. We have a 2-electron potential as well, where we can generate peroxide, and we have another one where we can do a 1-electron chemistry, but that one's very unfavorable. That one's very unfavorable. And what we're looking at here is trying to do epoxidation CH bond oxidation. And as we're doing this, we ran into something that's a little bit confusing. So you can see this, if I turn the laser back on. Can I turn the laser back on? Nope. How did it go backwards? Come back on, laser finger. There, okay, laser finger. If we look at this, we can see that there's a ruthenium-2 4 couple. So
And what are X and Y?
A direct,
Maybe everyone understands, I do not.
there's a direct, yes, it's okay. It's the direct ruthenium-2 to ruthenium-4 couple. So this is a Porbet diagram. This is a Porbet diagram. It's plotting the chemical potential, measured chemical potential as a function of pH.
Okay.
So the pH is down here. It's just hidden behind the little recording screen. It's labeled. It's just hidden.
Okay.
This is a 2-electron potential, which is weird. It's a little bit weird for reasons that'll show up. But what we need to do in our group is try to get that redox potential lower. We're trying to get it lower. So in order for it to use oxygen gas, we need the potential to be down here. Right now it's about here in this paper. So we have to go quite a ways. We have to lower that potential quite a ways. Down. So as we're doing this, we came up with...
Is it okay
backwards?
to ask questions as we
Oh,
go?
there it goes. It overwent. It overwent. Okay, if I push forward, it goes straight to this one. Then if I push backwards, it shows up.
Maybe
It's
there is
behaving itself weird.
up and down on the keyboard.
You can ask questions.
So what is wrong with these two ruthenium catalysts that you're showing?
Nothing wrong with this.
They work perfectly, but there is
It
too
works.
high potential.
It works quite well for oxidation, but it requires some chemical oxidant here. Chemical oxidant. It won't work with oxygen gas. And it only does epoxidation. It doesn't do hydroxylation, which is the reaction my group is more interested in. But
So it does or does not work in gas? I'm sorry.
it does not use oxygen. No, it cannot use oxygen gas.
Okay, so
Oxygen gas, the potential for oxygen gas is down here. It's down here, so it's not thermodynamically favorable to run with oxygen gas. You can't access the active site, the transition state, or intermediate with oxygen gas. You can't get high enough.
And are there any? So I apologize because I do not have background in all these things. So you may need to babysit and spoon feed.
No, it's okay.
So what are very lay language criteria for a catalyst? Like from the common sense, for me, it looks like it should be under-coordinated so that reaction can approach
it has some stuff drawn over here. There's stuff drawn over there. It's just cut off to make it the picture clearer.
But is it right that it should be under-coordinated? If it is octahedral, then it will not work as
Well, so
catalyst.
it's here. It has it is 6 coordinate, but one of the coordination sites is a water. One of the coordination sites is a water.
So where you
that
draw
deprotonates during
O,
oxidation.
it is it's water.
So it's water, and then when you oxidize it up, it loses 2 protons to make an oxo. So it gets oxidized. So yeah, maybe I should have talked more about the mechanism of this guy, but it's only tangentially related to the question I ran into.
Okay.
The problem. It's only tangentially related to my problem.
Thank you.
Okay. Yeah, I have to push the left arrow after the right arrow. Something is very odd. Because the one on the left is supposed to show up before the one on the right. So as we're doing this, we're using some empirical parameters to plan out the complexes we're making. So these were developed by Professor Lever in 1990. They're known as Lever parameters. And it's a plot of the predicted ruthenium-2,3 potential as a function of the sum of the Lever parameters, where the Lever parameters are an empirical value assigned to different ligands, different coordinating groups. And the theory that's based on, or the postulate that this needs, is that you can take an individual ligand, and as you add more ligands, they don't interact with each other at all. There's no weird second-order effects. They just add up their individual effects in a linear manner. And so the top is chloride complex, is complexes in acetonitrile. As you can see, very good correlation. The bottom is aqua complexes, so complexes in water, and they're a little bit more dispersed. But still very good. Very good. I wouldn't have predicted that would work the way it does, but it does. So that's a lever parameter. In 1996, Tom Meyer's group, doing ruthenium chemistry, noticed something that this could be extended to the ruthenium 3,4 couple. Ruthenium 3,4 couple. So on the left, everything is ruthenium 3,2. Here on the right, we're actually looking at is a delta E. So this on the left here is the difference between the ruthenium 2,3 and the ruthenium 3,4 couple. And on the bottom is our lever parameters in volts versus NHE. And you can see that the gap between the ruthenium 2,3, what happened to my laser? Went away. Come back, laser. The computer is doing things I didn't know it did. You can see that as you increase the lever parameter, the difference, the delta of energy between the ruthenium 2,3 and the ruthenium 3,4 decreases. It decreases, and then it starts to increase again. And then there's this region here that was predicted in 1996 where you would have actually a ruthenium, a negative difference between the ruthenium 2,3 and the ruthenium 3,4 couple, which means that the ruthenium 4 to 2 oxidation potential is lower than the ruthenium 2 to 3 oxidation potential. So this was an observation, and they explained it as being some balance between sigma donor and pi acceptor ability, which is a little bit vague. But this is the observation they made, that you would predict that region to exist. So what this looks like, if you actually just plot out the energies as a function of the lever parameters, if you look at the ruthenium 3 potential is linear. Has a linear relationship with the lever parameters, whereas the ruthenium 4 potential is nonlinear and actually ends up crossing the ruthenium 3 in this region down here. And then it crosses again. So that's weird. It's a little bit weird why the ruthenium 4 would go lower. I'm going to talk about history. So if we look back, this is the complex that has this potential, the one I showed you earlier that had the example of the epoxidation. If we look at this complex, this is the first ruthenium complex to be identified to have this ruthenium 2,4 couple, identified in 2010. So recently-ish, much more recently than it was predicted, about 14 years, to actually find something with this type of ruthenium 2,4 couple. It has this imidazole, pyridine, and 3 pyridines, and then the chloride is replaced with water when you dissolve it, so you have the water and then the oxo group. Their explanation is here, and it says a first look at table 2 shows that complex trans 3, which is that guy, is a particular case, since it is the only one presenting a bielectronic wave, so the only one with a 2-electron redox couple. This characteristic seems to arise from a specific balance between sigma donor and pi acceptor properties of the ancillary ligands, as expressed by the Meyer-Leber plot, which I just showed. And in this case, the anionic perp-O ligand looks appropriate to lead the Ruth3 state to disproportionation. However, the delta E value is not only governed by the ligands, but also by the geometry of the complex. Thus, a relatively good sigma donor, or less pi acceptor, ligand in a trans fashion with respect to the aqua ligand, lowers E1/2 with respect to the analogous cis isomer, hence stabling by the ruthenium 3 species. So the translation of that is that this occurs due to a combination of electronic and steric factors. That's what they're saying, which is not really a satisfying answer to me, because everything is a combination of electronic and steric factors, right? Are there factors other than electronic and steric factors that affect the energies? I don't think so. I don't think so. So that's their first explanation in 2010. In 2011, they made this guy. This complex, which now has an NHC here. So this is now a carbene-type ligand.
So the last one had a bi-BP? No.
This one has an imidazole. So, or pyrazole? Imidazole? I can't remember. One of them's. Nomenclature is not my strong suit, but now they've replaced this with an
Or they
NHC.
moved the N1 position.
So yeah, so now it's bound through a carbon. So this is a 9 N-heterocyclic carbon. They plot. Go back. I want my laser not tapping. Laser. Thank you. So if you now plot, look at the Porbet diagram. You can see again that they have a very nice ruthenium-2, ruthenium-4 couple. Ruthenium-2, ruthenium-4 couple. Coordinated, concerted to electron process, you can get the pKa's out of the Porbet diagram. So you see the Porbet diagram, you see the pKa's, and based on the slope, you can determine protonation state. So this one has, so where is my animation? Maybe the animation didn't make it. Animation apparently didn't make it for that one. Oh no, okay, same kind of guys. So similar guys, more NHCs, more complexes with nice ruthenium-2, ruthenium-4 couples.
So the cis-6, that
Yes.
one's just different conformation than the previous one.
So this is trans-3. So yes, trans-3
Cis-
and cis-6 are the same complex in a different paper.
No, but the conformation is different.
Yes, they've switched.
Yes, okay.
Yes. Yes, that is the difference. But it's a 6 instead of a 3 because the paper changed. The numbers are...
Yeah, I just wanted to make sure, because conformation is important.
Yes, it is. And then the trans here is this pyridal amine guy, BPA. BPA? Well, it is BPA, but it's not that BPA. It's this BPA, the inorganic ligand BPA, not the polymer softener BPA.
Can I ask?
Yes.
So it will be again a question on the level of spoon feeding and babysitting. So I'm just trying to understand the diagram. So the x-axis means that in your
X-axis
container you vary amount of protons.
is the pH. It's the pH of the solution, yes. So it's the
and-
relative
and
concentration
for
of protons in the hydroxide, yes.
And the complex that you are exploring, for each value of concentration of protons, it can exist both in like 2 and 3 different oxidation states.
Theoretically, yes.
So
but
we-
you
we-
apply
we-
a potential. So you apply a chemical potential. So where the line is, that's where there's a 1-to-1 equilibrium between the 2 oxidation states listed. So at this line, there's 50% ruthenium-4, 50% ruthenium-2 at the electrode. Below that potential, it's mostly ruthenium-2, almost entirely, very quickly goes to almost entirely. And above the line, almost entirely ruthenium-4.
Okay, so the oxidation state is driven by 2
It's
factors:
driven by
concentration of
pH
protons and external electric
applied,
field.
and applied current, yes.
So to do this, they did like a
Electrochemical cell.
cycle.
Yes, each data point here is a cyclic voltammogram.
That's okay.
Yes. So
Each data
each
point.
data point is a cyclic voltammogram.
Okay.
So you're taking a cyclic voltammogram, then you're adding a little bit of base or adding a little bit of acid, depending on which way you're going. Then you do it again. Then you
So
a
like
little bit, and you do it again.
at
Go.
like 0.5, there's 2 peaks in the cycle. Where I like
0.5. At 0.5, so that's an interesting thing. Here, there is only 1 peak.
oh
You would predict that there would be a second peak, but you don't see it.
okay.
They don't see it. You would predict the existence of a second peak. So you can calculate where it has to be based on this line and this line.
Okay.
But it was not observed. That's why there's no data points there. So there's data points here, point, but nothing there, just an extrapolation. Just an extrapolation. And in this one case, the gray one is the gray line, the black one is the black line. I tried to color code.
So it is electrochemistry at different acidity.
Electrochemistry is a function of pH, yes.
Okay. I feel a little better.
So this one, they had to now explain more because this is not the first one they found. It's the same group. Almost, it's in the same team. A recent report on DFT calculation states that a correlation can be established between the number of carbene units in a ruthenium complex and the ruthenium 2,3, ruthenium 4,3 redox couples in such a way that the higher number of carbenes, higher the E1/2 3,2 value, and the lower the E1/2 4,3. As the number of carbene units increases, the point where delta E is equal or below 0 can be more easily attained. In our case, however, a unique carbene ring has been shown to be enough to reach the ruthenium 3 disproportionation into the two complexes described. So they're referring to their previous work based on DFT that showed more carbenes equals easier to generate the 2,4. So we have to look at that work because they're not providing their own explanation for why. Because here they found only one was needed. If we look at the previous work, this is the previous work that they're citing here, you show that there's a linear relationship between the number of carbenes and the energy difference between the 3,4, which arises because of both a change in the stability of the ruthenium 2 and the stability of the ruthenium 3, and they find that you need 4 carbenes to get a concerted 2,4 redox couple. Except that the last slide had 1, and it was still showing. And if we remember the first example that they didn't have a good explanation for, it had none. No carbenes. So this paper studied a bunch of complexes with a bunch of different carbenes and came to the conclusion that there was something special about the carbene enabling this. With the one exception of the first one they found. So it says DFT calculations have shed light on the electronic origin of the degree of ruthenium 3 stability. It has been found that each carbene ligand lowers the change in potential by 100 millivolts, owing to the change of the monoelectric half-electron potentials E1 and E2 in concurrent but opposite directions. Except that that's clearly not the only thing, or it might be happening, but it's not the important thing. So in our group, we made this guy just to play. We made this hoping it would give us a 2-electron couple, but based on proton-coupled electron transfer. We were not yet looking in depth at lever parameters when we tried this. This ligand over here is commercially available, so we just threw it together. It was actually very easy to make. This was actually very easy to make. And we made a Porbet diagram. And we were very happy to see that we had a ruthenium 2, ruthenium 4 couple. And I have since edited this while I was making this thing, because I think I had originally assigned the proton locations incorrectly. So we have two deprotonatable groups, a water and the phosphonate ligand here. I think this pKa corresponds to the phosphonate, not the water. I initially assigned it to the water based on similarities to other complexes. But based on further research, I think it's probably the other way around.
Is that important?
That is a good question. That is a very good question. I think it probably is important. I think it probably is, and when we get into my theories, I can try to explain why that might be important. But when we then went to look at this, we determined the lever parameters and found that we just happened to be exactly where the lever parameters would predict a 2-electron concerted couple. So we're right here, 1.08. That's almost exactly at the bottom of that peak, right? 1.08. This is Hashini's work. And we didn't need any carbenes. There's no carbenes. So it can't be a requirement that there are carbenes to get this behavior. And in fact, this was proposed without any knowledge of carbenes. So if you want to say that carbenes are required, you have to say that the only way to get into this region is with carbenes, which might be the case, but then you would have some special cases with the lever parameters. So there's something happening here. something happening here. So the traditional way one would think about this, or the common way one would think about this, oh, I forgot to put in the citation. This is Tom Meyer's account of chemical research, is that because you have proton-coupled electron transfer, so when you're going from ruthenium-2 to ruthenium-3, you lose one proton from the water, and when you're going from ruthenium-3 to ruthenium-4, you lose another proton. Because you're losing protons, you are preventing charge buildup, and that is making the gap in energy be much less than it would normally be, because you don't have to build up a charge. So here, if you wanted to go straight from ruthenium-3 to ruthenium-4 without deprotonating, you would predict a very high potential. But if you can go straight, and if you were just going to deprotonate this, you would predict a very high pKa. But if you take the diagonal, you get a reasonable value. Yes?
Another spin feeding. Experimentally, if one wants to browse between these configurations, how do you mandate system to go from one to another?
So pKa of, actually this might be measured. So if you want to do this, you can make the aqua complex, and if you put it in an aprotic solvent, and use different, you can then measure this couple, right? If this proton has no way to leave. So if you take the hydroxyl complex, and you put it into something like acetonitrile, very dry acetonitrile, you can measure this potential directly.
By electrochemistry.
By electrochemistry.
So,
and when you do that, you run into a max.
This horizontal line is electrochemistry.
So this horizontal is just moving one electron. Okay. So you would want to measure it by electrochemistry.
Horizontal is electrochemistry.
Isn't all of this electrochemistry?
It's all electrochemistry, yes. But so the vertical is not electrochemistry because you're not moving electrons. You're just deprotonating. So this way you're just measuring a pKa, which you would probably have to do in an aprotic solvent because the pKa is above 14. You can determine it's above 14 in water, right? You just keep titrating and you never see a pKa.
So same as previous figures, beautifully named after some famous scientists. There are only two independent parameters.
There are only two.
Concentration of protons and external electric field.
Yes, and this is just showing at what the equilibrium constant is for proton and what that potential is for the complex, for that oxidation to leave, electron to leave. And so both of these directions are very unfavorable, but if you do them at the same time, it's not so bad. This explanation does not lend itself to predicting that you would actually have this potential being lower than the two one-electron potentials, right? If the reason this potential is so close to this one is just that you don't build up more charge, you would never expect it to actually become, this value to become less than this value. That doesn't explain why they would ever cross. That was the realization I came to this summer. And I don't have an explanation for why they cross, apart from the explanation that the other papers we just looked at gave, that there's some combination of electronic and steric effects that are related to pi donor, to pi acceptor and sigma donating properties, which is not very satisfying to me. So if we do look at the original paper again, say all they say is, as suggested by in figure 3, increasingly effective back-bonding ligands increase E1/2, mainly by stabling ruthenium-2. Increasingly effective electron donor ligands increase E1/2, mainly by stabilizing ruthenium-3. So that's telling us, or they are proposing, or Tom Meyer was proposing when he first noticed this, or the grad student first noticed this, that the reason we see this inversion is because of a very selective destabilization of ruthenium-3 and ruthenium-2 relative to the ruthenium-4. So for some reason, the ruthenium-3 is higher, is destabilized, and that's what's causing the ruthenium-2 to go straight to ruthenium-4. Why that might occur is an interesting question. Oh, come on, that's supposed to be the first one. Pi bonding effects in ruthenium-4 are dominated by the oxo interaction arising from d-pi-PO mixing, and I think that is correct. I believe that is correct, because that's the only way I can explain the fact that we see this ruthenium-2,4 with 3 different types of ligand scaffolds. The all-nitrogen ligand scaffold from 2010, the carbene ligand scaffold, which may or may not be its own special weird thing, I don't know, and the phosphonate ligand scaffold. So that's sort of like saying, oh, it's red. That's fun. When we do this oxidation, we're getting energy by forming an extra ruthenium-oxygen bond, except that extra ruthenium-oxygen bond is sort of an illusion, maybe. So it's known in the catalysis literature that this guy is actually maybe better described as the ruthenium-3 oxyl radical species. And depending on the ligand environment and the potentials, there's going to be more or less radical character on that oxygen.
But couldn't you just look at the total energy as a function of bond length between it?
One would hope.
Because then,
yes.
And then you could also look at like the percentage of electron occupation.
Right, that's what
But
people do.
Which bond? Only ruthenium to oxygen or some other? Like, what is your, maybe from literature, which bond contributes at most to definition of reaction coordinate?
Which bond, which
bond length contributes at most to a definition of reaction coordinate?
in the oxidation type reactions, or?
Yes, when we shuttle, I don't know the right language, on your slide number 10, with PSET.
This one?
Yeah.
This one?
When we travel between different points on this map, probably there is some bonds are elongating or contracting.
Yes.
So, and it is what can be used as reaction coordinate.
Yes. So this ruthenium oxygen bond gets shorter.
So
It will always get shorter because we're increasing the charge on the ruthenium, right?
You're going from a coordination bond to a chemical bond.
They're not always just coordination bond. Here it's always both.
But if you go over the diagonal, right?
Yes.
Path, this 0.78, it should be like a barrier along this bond, right? And number of hydrogens is different.
Number of hydrogens is different. Yes.
So
the diagonal
it should be
two things at once.
adding together distance from ruthenium to oxygen and distance from oxygen to hydrogen. And superposition of these two axes will generate reaction coordinate.
Right. But all the other ligands are also changing length. So everything, when you go from 3 to 4, all of the ligands get pulled tighter.
But in different measure.
In different measure, yes.
Because we can put percentage, and maybe
Yes.
percentage of this ruthenium to oxygen is like
Yes.
50%, oxygen to hydrogen is like 30%, and the rest a little bit. Okay, that makes sense.
Does that make sense, Levi? You happy?
Oh yeah.
Ish, happy-ish. But yeah, the point here is that it's not making a double bond in the same sense that making a double bond in an organic molecule would be, where you actually have a well-defined double bond. Here it's maybe a half bond, so I've seen people draw it as like a dashed line. Because the 1.5 bond-ish. Well, except that it's not 1.5, right? It's some number between 1 and 2, and how far do we want to take that? Because it's a Lewis diagram, and it doesn't like non-integer bonds.
So it's only one I'm returning back to the slide number 10 with this proton coupled. So there is only one hydrogen and one oxygen. So it's two-dimensional reaction space should be sufficient. Well, maybe not sufficient, but as a good approximation.
Maybe.
Okay.
I have no comment. That is too computational for me to.
It's not computation. It's modeling without computers.
Yes, it's too much theory for me to predict.
But it doesn't sound insane for you.
It doesn't sound insane,
Okay,
no. But the proton does have to go somewhere, right?
Okay. Yep.
It has to go somewhere.
To
So it needs
infinity.
the energy goes way up if you don't have somewhere for it to go. So typically you protonate a water or something, or you measure the energy difference between this guy. I have method stuff at the end, but obviously they did some method for this paper because they're doing DFT calculation and predicting the relative energies. And I know of a few techniques in use, but what you're talking about is actually modeling it as it happens, yes? Modeling this reaction as it goes and finding the intermediate and or transition states. Okay. Typically, what has been done to determine these values is just to measure the relative energy to the start and the end, and so you don't follow it. You just figure out where it starts and where it ends, and you get an overall delta G. Ish, a calculated delta G, or maybe a delta H. I'm not sure if they put in entropy or not. So questions, and these are not questions from you, this is questions I have for you. These are the questions I have for you.
Inverted questions.
Inverted, well, no, they're still questions, right? They're just
Questions in the opposite direction.
in the opposite direction, sure. The one I'm really interested in is why is this relationship between the potential of our complexes and the lever parameters linear for the ruthenium 2,3, but bendy and crossing for the ruthenium 3,4. That I have no explanation for why it should be. Or I have explanations, but I have no way of determining what's correct or if they're insane or not.
And is it, well, maybe it's too long to declare or write down, but the definition of this lever parameter, is it complicated? Is it
Nope.
possible to...
It's measured.
Can one define...
Purely empirical.
So it's
What?
like,
But what is composed of?
What is it composed of?
Yes. How is it measured?
You measure the potential of a bunch of ruthenium complexes, compare their ligands, and then fit.
so like a linear regression.
Yes.
So it's
Like a linear regression.
Like a slope?
For each individual ligand, you have to measure it. For any individual ligand, you measure it. So what we did for our guy here, I'm just going to tell you what we did for our guy here. Come back, there. We measure this value, right? This is the redox potential at a particular pH. You can extrapolate it to pH 0, I think it's 0, where the lever parameter is defined for. So you make a linear extrapolation. You define the total lever parameter as being, and then you find out where that is on the slope. Then you can subtract the values for these groups out. So chloride, pyridine, and terpyridine are all measured, or all defined values, to calculate a lever parameter for the phosphonate ligand.
So linear combination.
It's a linear combination.
So
Yes.
there is a formula. It's not empirical. There is a linear formula, linear combination of some measurements.
There is a linear combination of empirical measurements, yes.
Okay, good.
It is assuming that each ligand has its own lever parameter, and then if you add all those up, you predict
Makes sense.
sum of lever parameters equals that. So each individual lever parameter is empirical, and then you add them up to get the overall lever parameter for the complex.
Okay, yeah, thank you. Back to the inverse direction questions.
The other more important question. So the first one is something that's weird and potentially interesting on a theory level. The second one is more direct. That'll help us do some chemistry. Is why the heck are certain ligand combinations letting ruthenium-4 be lower than ruthenium-3?
What do you mean certain?
The ones I showed you. So, for example, this ligand set on ruthenium, when you switch off the chloride for water, causes us to have a 2-4 couple directly. So that means that the ruthenium-3 potential is higher than the ruthenium-4 potential, which from first principles makes no sense to me. And it's not that there are no 2-electron couples in nature. There are a ton of them. It's just that normally the reason you're getting a 2-electron potential is because you're doing an atom transfer. So, for example, you have things like periodate or any of the hypervalent iodine species. They do a 2-electron oxo transfer. So you don't want to generate an O dot radical. That's what's causing the problem. Ruthenium, in almost all cases, doesn't care about radical stuff. That's why it normally has a ruthenium 2,3 potential. So there's something that's making it unhappy with a particular electronic configuration. And I want to know what it is and if we can predict it. Because if we can do that, that's cool.
I have a comment.
Yes.
It will not answer, and it may sound stupid. It just throws direction of possible thinking. If we imagine classical charged sphere with different charges,
Yes.
0, positive, and negative, then neutral should have minimum energy,
Yep.
and going either to positive or negative will increase the energy.
Correct.
And projecting this model onto like quantum metal-organic complexes may have the minimum not at neutral but somewhere aside.
Somewhere instead of 0,
Mm-hmm.
you think? That's possible?
Mm-hmm.
It's possible for a plus and a minus separated to be more stable than just...
This parabola can be shifted with minimum somewhere else.
Oh, okay.
It's not an answer. It's just possible direction of thinking.
Not sure what that would mean. What that would mean in terms of our chemistry. But yeah, that is possible on a quantum level. But okay, yeah, because from classical, I approach things from classical because my brain works classically.
We did it for metal cluster with Sam Brown and Eric Hobby, and it was minimum not at 0 but very aside for heavily charged, and then it goes quadratically.
For like a particle? Yes. Yes, and that can happen for a particle because you're filling up orbitals, right? And then that's making them happy. And so then, yes.
But
The trick is here, that could very well be what's happening here. I think that actually has to be what's happening here by definition, maybe. I think. But why? Because normally it doesn't happen. The question is why, what is weird about, and this might, looking at these might also help explain that why these particle clusters are happy or not.
Could it be that the specific ligands that you have the mixing orbitals at various energies, and if you have a ligand field and you're splitting your state that you should occupy to make your 3+ goes higher in energy, so then like the doublet formation is not as easy to go through.
That is my first thought, but
it is another thing that spin multiplicity is another degree of freedom.
right.
That maybe you do not control explicitly, but it is there.
But I'm assuming
So this is 2,
that's so
6.
So it
3 is 5.
but it could be a high spin state or low spin state,
Doublet.
right? No, for yeah. So like
Or-
the spins or the octahedral splitting could be playing with it just right to have some not be able to occupy states where you can kick it out, but I'm not 100% sure.
Yes, the trick is that because we're going from a singly occupied, a half-filled orbital, the three will always have an odd number of electrons.
Yes. But where does, so like if we go from 2 to 3, where does the 6th electron go?
From 2 to 3, where does the 6th electron go? To your oxidant. It's gone.
Whoosh.
Swoosh. So if you're doing it electrochemically, it goes into the electrode and gets hucked over to the counter electrode where it reduces who knows what. Probably protons.
So
Probably
we change
protons.
total number of electrons in the simulation cell.
Yes.
Yes.
So it's not, when you're going from 2 to 3, you're not moving an electron within the complex. It's been oxidized. It's the oxidant is then reduced, and so yes. So
But if you go from a high spin state for 2 to a low spin state for 4,
yeah,
then you remove the 2 excited electrons. Right?
potentially yes. So you're always removing 2 electrons. The ruthenium 2 is never going to be high spin.
Okay.
The ruthenium 2 is, I don't want to say never, but shouldn't be high spin.
Is ruthenium 4 high spin?
Ruthenium 4 may or may not be high spin depending on how the orbitals are arranged. So if it's flattish and you put in, you end up something with a spin like that, which is not, it's
Okay.
high spin. It's spin 1 instead of, but it could all go up to spin 2, right? And the low spin would be spin 0. So it depends. It depends. It normally ends up in the middle.
I only ask because if you're at high spin, you have all electrons unpaired.
Correct. Normally doesn't happen.
Okay.
So the reason that doesn't happen is because we're on the second row. So this octahedral splitting is large. Octahedral splitting is large in the second row of transition metals.
No matter which ligands. Well, and
Large, so it is sometimes less or more large. I think you can force them if you really want to, right? But in our case, we're not doing that, I don't think. Unless we are, in which case that would be good to know.
but
So that would be a simple single point in
Right.
various ones.
but to your instinct, any ligands that you are trying keep the splitting large.
Right. So the ones that would cause ligands to, very, very low field ligands, we don't use those. We're using intermediate. So phosphonates and end-donor pyridine type ligands are all intermediate field ligands, which for a second row you would expect to still have a big gap. Yeah, the high spin, low spin thing is really a first row transition metal problem, which is one of the reasons we were working on the second row, so we could avoid running into those types of questions until we have something working already. Once we have something working, we can go to harder problems, but... and then which orbitals are actually doing this? Is it d orbitals on the ruthenium, or is it oxygen-based bonding or anti-bonding type orbitals? I don't know.
Well, I can be wrong, but intuitively, this
T2G?
yeah, they are above oxygen.
Oxygen. Which oxygen? The
I
p
know.
orbitals?
Occupied oxygen.
No.
Not always?
Not always.
Okay.
Not always.
So for some ligands they can dump deeper into.
So
But lower
oxygen
than
is
oxygen?
maybe up here,
Hmm.
and it's gonna hybridize with these guys.
Hmm.
Potentially both of those guys and form MOs.
Very interesting.
But then won't that affect the splitting?
Yes. Yes, it will.
Okay.
If it were a simple problem, I wouldn't be asking, right?
So the
I
most
asked the question that I knew to confirm that what I thought was correct.
What we'd like to do is predict combinations that we can test. So I have a bunch of known complexes. We can predict an unknown complex that has this behavior and then determine it's there. That'd be cool. That would be cool. And one advantage we have here is that we can actually measure the bond strength here of this guy experimentally. We can measure the ruthenium oxo bond strength experimentally.
Huh, really?
With Kent's resonance Raman spectrometer. We did some experiments over the summer looking at that, and we are confident we can do this
That's super.
electrochemically and reversibly, and so we can determine the frequency at which they vibrate, which lets you determine something about length and strength.
Do you have any facilities access to anything time resolved? Any of these reactions can be traced on short time scale, or you just
Yes. Yes, ish. So Siva has offered to let us use his fancy lasers at Bowling Green, which we could use to do this.
So you need
But we would have to go to Bowling Green.
Pfizer or just send
Yeah.
FedEx with
Probably send a student.
in a FedEx package.
In aesthetics, yes. Well, that's the cheapest way to send students, yes. Just put some popcorn in there.
FedEx package?
Mm-hmm.
Yes, he's going to FedEx you to Siva's new lab.
I feel like that would be the most expensive way to do it.
It might, yes, because they're shipping based on weight instead of person.
No, and they can sue you.
Oh.
So,
You get you to sign a waiver, it's fine. It's fine.
But
You want to graduate, right?
So which of the parts on this diagram can be tracked on time resolved facilities?
On this diagram,
Yes.
that one.
So you can follow it as it develops in time, within whatever picoseconds.
Actually, that one you can do. You don't need that one you can do pretty easily.
Here?
We should be able to do that here. I would need to consult with an expert in doing that. But I know some people that can do that or have done that. Because that you do is a fancy. You don't need to use light. You can use a fancy pulse sequence for the electrochemistry to measure the rates.
That's great.
The electron transfer rate, which is
Uh-huh.
presumably this. If
Mhm.
we assume that it is in fact a concerted process, and you're measuring the electron transfer rate,
Mhm.
you're measuring that reaction rate, right?
If you can think in this direction, it will be less effort and more outcome, rather than screening thousands of different
Right.
options. Okay.
So those are the questions I have. Right now, Hashini is working on some other things as well, but we have. So this came up because I was thinking, well, we have this data ready to go. If we can explain or propose something for why this is the case with some theory, maybe we can get a communication out of it quickly.
And your questions
Maybe.
extends to like a couple of weeks. If you do not get answer in 2 weeks, then
Well, I don't know how
your
long-
offer disappears.
I don't know how long it might take, but Hashini needs the paper, and I'd like it to be done before. See, in the optimal world, we have some nice theory, and then we can use that as preliminary data in an NIH proposal due in October.
oh,
In an optimal world.
October, like 1st of October or
25th. End of October. End of
Yeah.
October.
so like a month and a week.
It's like a month and a week. Ish. But obviously we need to interpret stuff first. But if we could include that as preliminary data, we could have happy times. Don't know if that's possible. I have this for technique. So in addition to the other technique, this is a 2012 paper out of Victor Batista's group at Yale. So I'm aware of this because I was there when this happened. Where they're determining thermodynamic redox potentials the same way we do it experimentally by referencing it to a reference molecule. So you take your oxidized species, you take your standard, and you transfer the electron, and you see what the delta G is for that electron transfer. And that's a way you can get thermodynamic values, and it works a lot better than previous ways. I don't think that's what they were doing in the 2013 paper with the NHCs. I think they were doing it their own way, just because there wasn't a large gap in time between there, and they didn't. I don't think they cited this paper. So if they didn't cite this paper, they didn't use it. But you can check.
Excellent.
So there are good ways of measuring just the potentials.
Great food for thought. And proton coupled electron transfer is a sweet.
Do you have questions for me? Is anyone interested in helping? Does anyone think they can help?
We'll discuss between us and maybe more brainstorming, but it's definitely something that can be done and not very long. Just no promises so that yet, but highly likely there will be something.
Because I think we're in a good place here to actually, if we can make a prediction, we can test it here. Not many places have the ability to test it the way we do here.
So,
thanks mostly to Kent and his fancy laser.
the parameters in your slide number 10 with psi, especially this barrier height of 0.78, it's different for each individual. It's
right. So this
only
is
for this complex, and you have like a range of complexes, and each of them has this activation, and each of them, if
each of
needed,
them will have this number. There's a bunch of these numbers. These numbers are less. Also, this is a different complex. So the one on the bottom and the one on the top are not the same complex. I don't think. They might be. Oh, they are. Yeah, 0.78, 0.78. Great. So I don't have to.
very good, very good.
But yes, so the advantage of working with ruthenium is you can find charts of relative energies and experimentally determined gaps between the d orbitals, for example. Because you can do that spectroscopically. So there's tons of experimental data to reference to. Probably too much experimental data to reference to.
So it's hard to find a sweet spot because everything is published.
Except that there's no good explanation for this. That's why I. That's a problem that the explanations I have found in the literature are not satisfying to me, and therefore I'm assuming they're not satisfying to other people.
What's the bigger dashed line that goes from like 6?
This one?
Yeah.
That's the 2 electron reduction potential for oxygen gas.
Oh, so you want to bring.
So we would like that.
down.
We'd like the solid line below the dashed line.
Okay.
So that's one. So we weren't initially. I found it really cool because we got the 2 electron couple, but wasn't super excited because it was too high. And when we tried to do catalysis with this, it decomposes. It has this little weak spot. That's an eraser, not a laser pointer. It has this little weak spot right here. But this is a commercially available ligand, so it was fast to make. And it gave us some nice data. And Austin's been trying to make it without the methylene. Hashini's actually made related complexes now that we are characterizing, that we want to make. So ideally we get a communication on this quickly, and then we have a full paper very shortly thereafter. And we all do a happy dance and have papers, and it's wonderful, and we get funding. And where we've replaced, instead of having this ligand here, we've replaced one of these pyridines up here with a phosphonate, and then we're having a BIPI and phenylpyridine and other ligands down here. Actually, a pain in the butt to work with because these phosphonates want to suck in water. They want a hydrogen bond to something, which makes life it's been making Hashini's life unpleasant. But she has one of the complexes very well characterized now. So yes, I couldn't find the Porbet diagram for that. I thought she did it, but maybe she didn't. We have a crystal structure and everything though, so that's getting ready to go too. I don't know if the
Crystal
one
structure, what? You can crystallize this?
not this one.
But some,
Actually, do we have a crystal structure of this one? We might have one of this one too. But of the related complex where the phosphonate is up here and the BIPI is down there. The pyridine is down there.
so they form crystal?
Yes.
Huh.
Oh yes.
That's cool.
Oh yes. That's how you tell what's bonded to what.
More questions?
Well, that took an hour, didn't it?
It was a pleasant hour. More questions, 1. More questions, 2.
I've been talking too
More
long.
questions, 3. Okay, let's thank
Okay.
Yeah, very good.
Yeah, sure. Keep the annotations. That's fine. I don't know if we want to save it with the annotations.
Okay.
Okay.
Yeah, many thanks for.
Thank you.